Well, good afternoon, everybody. Last lecture we spoke about Peirce's model. Peirce's model introduced the general logic of the problem of strand distribution in different gauge lenses. The strand distribution over the different strand lengths. Nevertheless, Mr. Peirce used some set of assumptions. One of assumption was independent strands. Based on idea of Peirce, each short fiber portion, strand of each short fiber portion is independent to each other. This independency. When the experimental works was doing, the results was other. The strands of short segments are not independent. If one segment, one part, length L0, have relatively high value of its strand, that the probability that the neighbor will have also a little higher than mean, than average value of strand is the probability is higher than that this is absolutely independent. You can imagine also intuitively that this relation is possible good to see, because if in this yarn is good oriented fibers, then by neighbor also the fibers will be good oriented and something so. So that the independency, this is a problem which is not valid. Weak's link principle. Weak's link principle, some authors, I spoke it in the last lecture. Of course, we must work with gauge lengths higher than Longe's fiber lengths. When we use shorter, then the Weak's link principle is absolutely out because we measured something other. Nevertheless, when we use such, then different authors have different meaning. At most, they are meaning that we can accept the Weak's link principle as a good theoretical assumption for our modeling. The third is normal distribution of strand of short specimens. In a short specimens, the experimental results show that often this assumption is acceptable. No, every time, but often yes. Based on, what is the Hygi's differences? It is the point one. Point one, it means independent strands. No, they are not independent. So it was necessary to create some more general model in which the among the short fiber portions, among the strand of short fiber portions, was some dependency. Let's imagine a yarn symbolically divided to some portions length L0. The distance from here is 1 times L0, 2 times L0, 3 times L0, I minus 1 times L0, and so on and so on. Yeah? Each portion, each segment have its own strength S1, S2, S3. So we obtain some series of quantities S1, S2, S3, Sk, and so on and so on. Yeah. What is the strength of some fiber lengths in which are the segments from ith segment to ith plus k? Yeah. Let's imagine some length in which is k plus 1 segments from subscript I to j equals 0, j equals 0 to j equal k. Yeah? How is the strength? No, it's a minimum from strengths, from all these strengths, isn't it? Mathematically say this is a minimum from this set. Is it clear? Yeah. The experimental, our experimental work was following. The table illustrates an experimental values. We had some instrument which help us to use 5 centimeter gauge length, L0 equal 5 centimeter, and we measured strength. Then second 5 centimeter was a technical length because some length is necessary because in both jaws we must clamp the yarn segment, isn't it? Yeah. So in our system it was so that the jaw was here, and we measured strength of S2. Then the jaw was here, and I don't know here, and we measured the strength of S4, and so on and so on. Yeah. So one beside the other, we knew the distances between neighbor portions, length 5 centimeter, and then we evaluate how is the strength of longer lengths, because we had this small. We obtain experimentally. We obtain, this is immediately measured, it's from different gauge lenses on breaking machine. Same yarn, and we obtain such values, mean value and coefficient of variation. By 5 centimeter, it was 21 centinewton per tex and CV around 12%. By 700 centimeter, which was longest what's possible in our breaking machine, we obtained 18 centinewton per tex and 9.5% CV. You can see that really, in reality, the strength is increasing of gauge length. This is the gauge length. In increasing of gauge length, the mean value of strength is decreasing, and the CV, coefficient of variation of this quantity, is decreasing too. You can see how is the distribution by 50 centimeter, by 500 and by 700 centimeter. It was same yarn, but different know-how for measurement. One time it was 5 centimeter gauge length, then 500, then 700. Yeah? Can you see this histogram? How is going from left-hand side? This histogram is recalculated to the standardized values. Yeah? So you can see this linear transformation which we so that you can see it is going to left and more to the left-hand side in opposite to this this Gaussian standard probability density function. Gauss the idea of a Gaussian distribution in short lengths, in this case 5 centimeter lengths, is relatively good, as shown this example. It is same yarn and quantile plot. Maybe you know what is it. There's some graphical system through which you can watch if this or that distribution is or is not enough Gaussian. You can see that the dominant part of points are lying on straight line, which say us that this distribution is practically very good, compatible with Gaussian distribution. Yeah? So the idea of Gaussian distribution can be. But how it is with dependency and independency? We use so-called autocorrelation function. Do you know what is it, the autocorrelation function? Maybe you know what is it, the coefficient of correlation. You know what is it, coefficient of correlation? You know it, yeah? So, good. Let's imagine our yarn. We measure, let's imagine theoretically we have the set of quantities S1, S2, S3. Yeah? We can create some couples. S1 and S2. Second couple, S2 and S3. Third couple, S3 plus S4, and so on and so on. Every time this couple of quantities represents two parts in which the distance is 1 times L0. Yeah? Well, and from these couples, we can evaluate a coefficient of correlation. Is it possible? Yes. We evaluate it and we say, yes, this is the coefficient of correlation for distance of these couples of strands 1 times L0. Yeah? Nevertheless, from the same set of experiments, we can evaluate we can create another couples, S1 and S3, S2 and S4, and so on. The two values in each couple have the distance on the yarn 2 times L0, isn't it? Is it imaginable? We evaluate coefficient of correlation, and we can say this is the coefficient of correlation for the distance 2L0. Similarly, from the distance 3 times L0, blah, 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 to all possible distances. And we can create some graph. We can, on the abscissa, we can give the distance between our couple values, 1 times 0 or 2 times L0 or 3 times L0, that is distance. And on the ordinate is value of coefficient of correlation. Yeah? And we obtain such points like this, which are here. It's one real example. Can you imagine this way? I hope yes, it's possible. Evidently, the coefficient of correlation when the distance is 0 must be 1. Because when you have couples from one value and the same value, the second value and the same value, then the correlation of couples where both values are every time same is 1, isn't it? So that this point is also one of point from this coefficient of correlations. And the function which say us how is the change, the coefficient of correlation in relation to the distance is a correlation function. We call it as a correlation function, nothing more. And because both these values are from the same yarn, when we speak about a yarn, it can be quite other problem, but from the same set here, from the same yarn, now the first from blue yarn and the second from yellow yarn, yeah, another yarn, the same yarn, Therefore, we must to call this function as autocorrelation function. Yeah, it's correlation in the same yarn. Therefore, this is the autocorrelation function, and the experimental trend of autocorrelation function is given by this black points here. It's real experimental result. This is experimental result. Now, how to formulate a model, mathematical model, stochastic model of this autocorrelation function. We used set of ideas. I want here only present the name of these assumptions which we used. We think this, the series of our quantities, it was S1, S2, S3, and so on. This series is some stochastic, represents some stochastic process. In the theory of stochastic processes are known following terms: stationarity, stationary process, stochastic process. I want to explain it only very vague, only very intuitively. So if somebody of you know it in this mathematical precision, then please apologize me. Stationary is a process when it's a random process, but it oscillates around some quantity, around some value. Yeah. For example, a process which permanently is random, but in the general the trend is increasing, is not stationary. Yeah. So we assume it as a stationary process. The second is ergodic process. Ergodic is intuitively very difficult to say. Very intuitively I can say it's normally imaginable what we understand, what we feel under the term stochastic process. Markovian process, it means that the influence of the following value in our series, the influence of following value have only the value which is immediately before. So the strand of, I don't know, 12th segment of the yarn is influenced through the strand of the 11th, but no influence through segment number 3, for example. Yeah. Only the neighbor can influence the following, the probability of the following value. Similar processes have named Markovian processes. And finally is Gaussian. It means that we will use a distribution according, normal distribution according Gauss. Well, using this type of process and using set of mathematical tools, different, we can derive that the autocorrelation function must be exponential curve, one exponentially decreasing curve. Yeah? It's a mathematical result of process which is stationary, algorithmic, Markovian, and Gaussian. Well, nevertheless, our experimental result don't correspond with exponentially decreasing function. Therefore, we said, okay, this is not well. In reality, it's a little harder. The real situation seems a little harder. We start to think about such two independent processes, but having another parameters. And then we obtain very good result. It is shown in this example on this picture. One process have this character of autocorrelation function. It is in this moment, I don't know, roughly 35% this process. plus 65% at the second process, which is going from here to here. The autocorrelation function is slowly decreasing in one case and quickly decreasing from the other case. Yeah? And sum of both together give the resulting thick curve, which could explain our trend measured in our laboratory. What it means from point of view of logic? The variability of our strands in short lenses, S1, S2, S3, which was in our first picture, is a result of two independent influences. One influence decreases very slowly, second decrease very quickly in autocorrelation function, or the correlation decrease slowly and the second quickly. How is the physical sense of these two influences? Nobody knows to this time. Nevertheless, one of them may be this more quickly downgoing part. It's a result of variability, of mass variability of the yarn. We compare it with results which we obtain from Uster tester, mass unevenness, yarn mass unevenness. We recalculate the primer values from Uster apparatus to autocorrelation function. It is also difficult. Okay, jump these difficulties. And we obtain something which was similar to this curve. But what the sense of this influence? Nobody knows. We can have a lot of hypotheses, but no one is verified. In each case, it exists two independent influences which create both together the resulting variability of strand of our portions on the gauge lens L0. Okay. Based on evaluation of such experimental curve, we obtained parameters through which is possible calculate all other equations, and finally to calculate the probability density function or standardized version for different gauge lenses. We use the simulation method, because the analytical version is very, very difficult. Therefore, we use the computer simulation. We simulate the strands S1, S2, S3 like this here using computer. We give in computer corresponding equations and parameters, and computer is possible then to produce the strands S1, S2, S3 with the same distribution as in original yarn. This computer simulation. Then we can evaluate also the distribution on strands for longer lengths. Easy. From length 10 times L0, we produce based on our software. We simulate first 10 values and minimum next link. Minimum of these 10 values is the strand of length, the first length 10 times L0. Second 10 values generated from computer represents the second long length, and minimum value, it is the strength of this one. So using this way, using this simulation way, we can simulate the set of values, of strand values for different lenses, and there are the probability density functions for such. For 50 millimeter it is here, from 500 millimeter it's here from computer, and from 5,000 millimeters, 5 meters, it's here. You can see similar effect as by Peirce's model. Yeah? Wow. And now how it is with when we have this set of values, set of values which obtained from computer using this simulation, set of simulated values, we can evaluate it from this set same way that in laboratory, mean value, standard deviation, coefficient variation, and the standard statistical characteristics. And when we had this, we proved to apply also similar equation than Mr. Peirce. And we obtained following expressions. They are based on our experiences for cotton yarn. They are good. We can use it. Nevertheless, the exponent here is now 1 by 5, then 1 by 9.3, and this coefficient is 5.3 and was 4.2. Peirce derived it on for his model, individual independent independent yarn portions. Now it is for dependent. We call it as SEMG, stationary ergodic Markovian and Gaussian process, yeah, or dependent, so that we obtain another parameters which can approximate the resulting values, like here. What's interesting? Professor Žurek, a very known name in the theory of yarn, in this year very, very old man in Poland, in the town Łódź, in University of Łódź. He measured this problem too, and he derived empirically the value, this exponent as 1 by 7. 1 by 7. Based on our experiences, we have 1 by 9, but it is evident that reality have higher value when we approximate the reality through this equation. The reality need to use higher exponent than is the Peirce's exponent, 1 by 5, derived theoretically only. Yeah? Some small story. When Professor Žurek was 70, it was, no, maybe 75, I don't know, 70 maybe. It was a conference, international conference in Łódź, and I present here some contribution why Žurek's value 1 by 7 is better than earlier Peirce number 1 by 5. Because this theory say it theoretically. Yeah? And how is now the resulting the example of the results? Points are same as earlier. Points are experimental points. Mean value and standard deviation. Earlier Peirce model, it is the red curve here, this and this. Now when we use our model which accept the mutually dependence of yarn segments, we obtained here the blue curve. You can see that this blue curve is a little better than the earlier red curve. Yeah. So is a short overview, nothing more. Short overview over this model of yarn strength as a stationary ergodic Markovian and Gaussian process. we call it SEMG process, which bring a little better results. Nevertheless, full derivation is relatively long and need to use quite no easy method for derivation. Therefore, I want to recommend you, when such problem will be, especially for somebody of you, actual, I recommend you to call or invite Dr. Dipayandas from IITD and ask him, because he 3 years works on this theoretical as well as experimental concept, and he is in each details very good informed. Well, and this is all for the problem of Jan Strand, or for the problem of all textile questions, about which was my set of lectures. My last words are acknowledgements. I want to say, to thank at first to my colleagues from our university, namely from the Department of Textile Technology, who helped me in my research work very much. Then I want to thank to Professor Ishtiak, your known professor for the Department of Textile on Indian Institute of Technology, Delhi, because he inspired me for preparation of this set of lectures. And third, I want to thank to Dr. Dipayandas, today's assistant professor on the same department, who was first reviewer and English corrector of all of my lectures. Well, but my greatest thanks goes to my dear wife, which, I'm very sorry to say, she breathed her last on February in 2004. And he inspired the whole my professional work in whole my life. Maybe this woman is my wife. This person is known for you. It's Dr. Dipayandas. I am here. You see only my professor mask today. This is my nature face here. And it's from my trip to Isera Mountains, which are the mountains by our town, where I am living and where is our university. This trip was when I was 60 years, isn't it? When I was 60 years. So this is my thanks. I thank also you, because you was a very good auditorium for me. I wish you good luck, successful study, and all good what you want. Thank you.